So the next speaker is Volker Roeber from l'Université de Pau et Pays de la Dour.
I understand Jonas is going to share the screen. Is that right?
Wait.
Yeah. Hi guys.
Hi everyone.
Okay, good. So are you going to sing?
Yes, exactly. You got it. No, I mean it's Friday afternoon, so we decided to share the workbook.
I think that's perfect.
Let's just share the screen. Can you pop up the presentation? Okay, do you see what we see?
Not yet.
Partager.
Okay, perfect.
Is that better?
Yes, we can see the slides. So next speaker is I think Volker Roeber from UPPA, but also Jonas Pinot and Simon Lasteri. So please, guys, go ahead.
Thank you, Mario. Hi everyone. Thank you for giving us the chance to present some of our work. I'm Volker Roeber, and I'm here with two of the PhD students in our program, which is Simon Lasteri and Jonas Pinot. We're going to share the presentation for the next few minutes, and we would like to take you onto a small virtual tour to our study area here at the Basque Coast. You see in the background how this looks like, and we would like to address a common problem that possibly has been overlooked in the past a little, and that's actually the variability of waves along the shore, like in a spatial and also in the temporal sense. And we're going to address this from two different perspectives, wave energy and also the run-up of individual waves. So if you have been to the area, you know how this looks like. We're basically located in the southwest corner of France, here in the center or in the corner of the Bay of Biscay. You know, the North Atlantic is a pretty rough environment. Area here is very exposed to large open ocean swells, not so much to wind, but very large energetic swells, 18-20 second peak period in the wintertime. And also the coastline is actually quite irregular, not in the sense of the coastline itself, but of the underlying underwater bathymetry, which is the result of the Pyrenees that extend further down under the seafloor. Ocean is relatively deep here. We have a submarine canyon to the north, and we have basically the full mix of features like embayments, river mouths, engineered natural beaches, cliff coasts, sandy coasts, and also some of the very rough and irregular features of the bathymetry. So in our chair, we conduct coastal research. We address basically two main axes of research. We develop numerical models, and then we apply them to understand processes, physical processes in the nearshore environment. And this is what we're trying to convey to you today. We look at two perspectives. One is overall regional scale wave energy, and the other one is coastal safety, which looks into wave run-up. And in both talks, you're going to see that we're trying to highlight the variability at different scales, different length and different time scales, one with respect to the wave climate, and the other one with respect to actual local individual waves that compose in the run-up. So I'm going to turn over to Simon, who will talk about wave energy on the regional scale.
So when I did my review about the wave energy assessment, it appeared clearly that most studies were mainly focusing on mean values. On one side, you can see on the top figure that was the result of a 40-year wave incast analysis. And the result was analyzing mean values. And in the down figure, we can see another wave energy assessment trend analysis that was done in 2017. And here what appeared is that this analysis had been carried out on a 75-kilometer grid. So here the question was how these studies could really assess the variability of a wave energy climate, averaging values of a very long period of time or over large distances. So in my study, I focus, as Volker explained, on the South Aquitaine region, over a computational domain of around 80 kilometers, with a major bathymetric feature being the Cabreton submarine canyon. So I used the SWAN spectral model to carry this analysis over 44 years. This model was forced with full spectral data. And the data was stored every 3 hours. So we have a 44-year handcast analysis with data each 3 hours. The model was validated against with a coastal buoy measurement in Bayonne, more than 20 meter depth. So we could see a good agreement of the simulation versus the observation. And in terms of results, here I first plotted what is usually done in wave energy assessment, being the mean wave energy flux over the full period. So here we can see that the wave energy appears to be, the mean wave energy flux appears to be higher north of the submarine canyon, being the submarine canyon being in this area. So we can really see the zone divided into two areas. And this spatial variability also is visible in terms of temporal variability. When comparing the seasonal wave energy flux, we can see that in both summer and winter, we have a spatial gradient between the north and the south, with a very localized hotspot in the near shore. But in order to go deeper in the analysis, we followed a method seen in the literature, which is the coefficient of variation, being the computation of the standard deviation of the average values, the monthly average values of the wave energy flux, normalized with the average over the full handcast period. And here as well, what we can observe is that the variability is higher in the northern part of the domain. So we can see, interestingly, that the variability is the highest where the wave energy flux is also the highest. So we had a strong level of wave energy, and in this region, this is also where we have the strongest variability. And in order to assess the variability inside a year, we use the seasonal variability index, which is comparing the winter months with the summer months. And here as well, we conclude the same thing, that the variability is higher where the resource is the highest. We have a 44-year handcast, so the idea is not only to address the issue of the spatial variability of the resource, but also the temporal variability of this resource. So here we computed the annual mean wave energy flux over 44 years for each year at two locations located in more or less the same depth. So one off Bayonne in the southern part of the computational domain, and the other one in Cabreton located in the northern part. So we can really see a difference in the level of wave energy flux between the northern and southern part for the mean wave energy flux in the subplot A. And using this annual mean wave energy flux values, we computed the interannual variability between 2 consecutive years. And here as well, we can see that the variability is higher in the northern part of the region. I wanted to be sure that the maximal values were not the reasons of this variability, because as I said previously, in the wave energy assessment issues, in order to make the data readable and understandable easily, we tend to use mean values, but these mean values are actually hiding some part of the information that we computed. So I wanted to make sure that those mean values were not that much affected by very high extreme values. So here we have the maximum values and the 98th percentile. So we can see a big drop but still no long-term trend is visible either on the annual mean values, the interannual variability, or the maximal values. So in conclusion, we could see that we have a strong spatial variability at the regional scale, but also on a more localized scale. Here we can see in the left subplot here that the variability is also quite strong at the level of few hundred kilometers. And we have a strong temporal variability with a high inter-annual variability between 2 consecutive years and more, but also inside the same year between the 1 month to another or from one season to another.
Okay, so as Shimon just explained, we used a large numerical domain, unstructured grid in Swan. And by just using a relatively coarse grid, we weren't really sure whether we resolve all the features. And we noticed there are some minor hotspots where the mouse is actually located. And we recomputed some of the key events along that area at a much higher resolutions, also with Swan. And we found that this spatial variability, like these strong fingers of energy hotspots, they are actually present at a much higher level. Of course, this is still with respect to a phase averaged model, a Swan model, looking at a wave by wave scale. With a phase resolving model, it becomes even more extreme. And that's what Jonas is going to focus on. He's looking at a study at Grande Plage de Biarritz, which is in the corner here between these two headlands.
Thank you. So exactly as Volker said, in my work, I'm focusing on the study site of Grande Plage in Biarritz. This study site was chosen as it's very typical from the Basque Coast. It's very urbanized, and it's within a mesotidal environment. It's an on-bay beach. You can see on the figures the fact that it's very urbanized, and here how close the wall is from the shoreline. And it was also frequently subject to overtoppings event. Here you can see a tentative of protection and an overtopping event on the right in front of the Casino of Biarritz. And that's why this study site came up, as it was there were high stakes. And there were visual observations saying that the runup could be locally very high compared to other locations along the beach. And that's why motivated this study of alongshore variability in the first place. So we focus on the runup as a proxy for coastal risk assessment. And what is usually being done right now is the use of parametric formulations that are formulations that relate offshore parameters, such as, for example, the significant wave height or the peak period, and morphologic parameters such as the foreshore slope to estimate the runup. It's usually fast and easy to implement, but it has limitations, especially, for example, in environments, complex environments such as unbathed beaches, where the impact of the headlands are not taken into account. Also, beaches with complex 3D features, such as rocky islands or strong bathymetric gradients, which is our case here. So that's why we decided to use a numerical model to try to estimate the runup as closely as possible, and also to investigate the processes that would lead to this alongshore variability that was observed during energetic events. So first, the model that we chose to use is the one from Volker, and it's a Boussinesq type model based on the no-go set of equations. It uses the conserved variable formulation and is a shock capturing numerical scheme. In the first part of my work, we reproduced an experiment that was done in the GWK wave canal in Hanover, Germany. The experiment was performed by Chris Belenkensop. And so it was a single crossover profile, and waves were measured using resistive gauges. And the important aspect of this experiment was that it used a LiDAR scanner to capture the surf and swell zone processes. So we saw in the previous presentation yesterday the use of the LiDAR scanner and how accurately it could capture the wave profile. So it was very interesting to be able to have such a detailed description of the free surface to compare to our model. And we used the time series measured at the first gauges as input for the model, which means that we knew the phases, which has, as you will see, which is a big aspect of the work. And what we found is that the model was able to capture wave transformations and swatch processes very closely. Here on the left figure is a description of the experiment. The gray shaded area is the LiDAR scanner area. And on the left, the first two plots are a comparison of the model in blue and the observations in red at WG2 and 3 gauges, and then the bottom figure is the comparison of the shoreline, the swash oscillations. So you can see that the match is very good, and the use of the phases really make sure that we can compare the time series between the two. And we did some tests with for example, random phases, and we found that even though it had the same energy within the input spectrum, the results were fairly different, and it was really hard to get a match as good as when we use the original phases, which is interesting, especially as we know that when you use model in real life, usually you have data from, for example, a spectral model or a wave buoy, and you usually don't have any phasing information. So it has to be put into perspective, I would say. So then in my current work, we are using a field campaign for the model validation. So here you've got the configuration of the campaign. So we used pressure sensors in the near shore, one seabird located at about 12-meter depth, and then 4 RBR pressure sensors in the intertidal zone to measure wave transformations. And then the swash measurements were based on video imagery. The video station was located here on the southern part of the beach, and it recorded 4 transects at different longshore locations along the beach, and to measure the swash time series for comparison with the model. These are the conditions that were observed during the campaign. So it ranged from lowly energetic with 1.2 HS of 1.2 meters to quite energetic with a 4.5 meters HS. And you could see that also the spring, we targeted spring tide as high water level in combination with high tides in combination with energetic events are usually responsible for these submersion events. And so you can see that the tidal range is large. And that's why during some, for example, at low tide, there were no pressure sensors data, as they were all in the intertidal zone and the upper intertidal zone. And same goes for the video camera. They were targeting the upper part of the beach, which is usually where the submersion happens. So there were as well no data. So this is also a case where the numerical modeling implementation is interesting, because then it can cover up for the data that we miss under these conditions, for example. So the setup of the model is as follows. We used a regular square grid of 3.5 meters, and we used SWAN outputs as offshore boundary conditions. And this is an extract of the bathymetry, and you can see how complex it is. So the video transects are located on the southern part of the beach here. You can see the presence of rocky islands and also a rip channel here, shoals in the middle, and all of this makes it very complex for parametric formulation to estimate the runup. So that's why we use our model. And I can show you now an animation of the computation. So I hope you all see it. So you can see the wave propagating within the embayment, and what you can see really easily is the impact of the rocky islands at the different locations. And our assumption is that these rocky islands, in combination with the strong bathymetric gradients that we observed, are responsible for the longshore variability, and that's what we want to to investigate once the model is properly validated. So now onto the model validation. So first we validated the model for wave transformations at all the pressure sensors location. On the left graph, you have the short wave frequency band, and on the right graph, you have the infragravity waves. So you can see that there is a satisfying correlation for both frequency bands between the observations and the modeling data. You can also note an overestimation here. The black squares, they denote the seabird data. And so we note an overestimation of the model at the seabird location for highly energetic event. And these observations was the same as well for the SWAN modeling. So here it highlights the complexity of the modeling of the configuration, because in both models there was this overestimation. So this is still under investigation, but for now we haven't found any satisfying conclusion for this to analyze this error. So then this is a comparison of the wave spectra over at different depth. So over in blue is the model, and red is the observation. You can see that the model generally captures well the decrease of energy that you see due to the depth-induced wave breaking of the high frequencies in the surf zone, and the fact that part of the energy in the high frequencies is transferred to lower frequencies. Which gave us confidence into using the model for wave transformations. Then we used it for the main purpose of this work, which is the SWASH study, the runup study. And here you can see a comparison of, so this is the total significant SWASH height here associated with the high frequencies and lower frequencies. And you can see that once again, the match is overall satisfying, even though an underestimation of the model is noted, which, and also the shortwave SWASH appears to be the one that is the most challenging for the model, as you can see here on the R-squared values. And we noted as well that the observations were also very sensitive in the high part of the spectrum due to the way that you extract the time series, and it was based on a color contrast method. So here we really have I would say inaccuracies of the model on one part, but also the inaccuracies of the observations on the other part, and it's really complicated sometimes to know which one is to blame. But overall, the performance was still satisfying with the RMSE of 42 centimeters, and when normalized, it's about 60%. Especially when you see the range of values that you can have in the SWASH goes from as low as 80 centimeters up to almost 3.5 meters. So it's a very wide range of values that you can have on that beach, which proves that it's a complex configuration. And so to finish, this is a time series of the significant SWASH height at the different longshore locations. So from top to bottom is from south to north, and the conditions during the campaign are shown reminded in the first subplot. And you can see that the model and the observations are well phased, and you can observe the strong temporal variability. For example, if we look at this location between noon and then when the tide comes in, the SWASH, significant SWASH height is doubled, whereas the significant wave height and the peak period remain the same, showing that the tide is really acting as a strong key parameter. And same goes for the spatial variability. You can see that if you compare on the first day at noon to this location to any other location, you see that you get twice as much SWASH as at the other location. So this location being the most southern one. So this also shows that the morphology and bathymetric features surely have an impact on the SWASH variability. And in the future work, we want to investigate more closely how each feature impact the run-up.
Okay, very nice. Let me just wrap up what we've heard in a few words. So we looked at the Basque Coast here in the southwest corner of France, and we've seen that there's a strong variability of wave energy on different time and spatial scales. And that variability has an important impact on either wave harnessing and wave energy conversion, and also coastal risk assessment. So from the wave energy perspective, we see that there is a strong influence of the submarine canyon that separates basically this area into two zones, a more energetic northern part and a less energetic but very irregular southern part. Averaging over time makes data understandable. That's quite natural, but it somehow removes a few critical components, and that's important to understand. We found that areas with overall high energy levels also show very strong variability, and that just adds more complexity to the problem. So now the question is, for example, if we want to use these model hindcasts to better assess locations or even devices for wave energy conversion, to what extent and how do we have to take this variability into account? So this is an open question. With respect to coastal safety and coastal risk assessment, we saw that there's a significant temporal variability induced by the tides alone, so on a daily basis, on an hourly basis. We also see that there's a strong longshore variability as a combination of the influence of the bathymetry and the overall wave regime in the zone here. Phase resolving models can do a good job as long as boundary conditions are known. And that's, I mean, it's somehow trivial. It's not really surprising. For example, for the experiment we've seen, we almost get a perfect match if we know the bathymetry, let's say the underlying tank geometry and the input time series and phases and everything. However, by driving the model with a spectral model or integrated quantities like just HS and TP over a 2D domain, this adds a whole bunch of more complexity. So in the end, it leaves us with the question, to what level do we actually need to compute the runup with a numerical model? Or under what conditions can we use reliable, or can we use reliably formulations like the one from Stockton, just empirical runup formulation that give us a relatively safe estimate. So this is something we're trying to understand. But as you can see, this area is a good opportunity to study all of these aspects. And I hope you have a few suggestions or comments, and we're happy to take questions. Thanks a lot for listening.
Okay. Thanks a lot, guys, for this talk. So we have plenty of time for questions. Are there any among the audience?
I have a question about, very nice analysis. So you got nice space-time data. I wonder, I would like to know your ideas, or what you think about. You're familiar with the theory of Borgman regarding the storm analysis. How to define a storm in the time domain. So do you think, it would be interesting now to try to extend this concept to a space-time storm. So, I'm not aware of, any recent work, to best of my knowledge, that, they try to study also the space variability and of a storm and try to characterize it statistically. So do you think this is worth doing it and come up, with, or, if you have some other ideas, since you have space-time data, so what is your perspective on this kind of concept? Are you familiar with Borgman? Is the classical, is the standard storm analysis. The time history of a significant wave height. That looks like a pyramid. You can have a triangular storm. There is all the work by Felice Arena and Boccotti and many others. That they try to. So I wonder, if you look at at this kind of approaches, and if you have ideas on how to extend it to the space domain, to add so I'm just curious to hear from your perspective on this.
Excellent point. I think this is that's very important to look into. We'd like to use the opportunity here to ask for the citation and or PDF of the paper. We are not aware of that. We probably should. That is totally right. Please feel free to point this out. I agree that it is important to look at the change of the storm and the spatial temporal impact on that. We noticed that when a storm passes, it mostly changes not only in its, let's say, overall energy level, periods long in the beginning, reaches then the peak at significant wave height, and then kind of decays a bit on to the end. It also has a strong impact on the directionality, and this is something that we observed here. As I said, symmetry is relatively steep and deep here. However, by the time the swell hits the coast, it has retracted quite a lot, so the directionality is not that strong. But due to these high energy features, these hotspots of energy levels, we notice that as the storm passes and the directionality changes, these fingers still appear, but they focus wave energy to different locations. So you basically have a different directionality of the hotspots that actually then reach the shore and can lead to a strong variability of the runup. But please,
I'll send you. I'll find the paper and I'll post on the chat. I'll share it on the chat.
I'm sure others are also interested. Excellent point.
Thank you.
Great.
Okay, there are a few questions from Kevin Martin. So first one is, have you guys tried to reduce the grid resolution to improve the swash predictions? Because 3.5 meters in the swash region seems pretty high. The second is, what is the reconstruction method that you use for the pressure transducers? Because the uncertainties will be largest during energetic events. And then there's a suggestion about a paper on costly engineering by Julia Fiedler that regards the accuracy of boundary conditions.
Yes, I know that paper.
Okay, yeah. So I think it's focused on my work. So thank you for the questions. I followed the presentations, the previous presentations, so I know some for example, for the reconstruction for the pressure sensors, I know that there was a presentation about that as well. We use the linear reconstruction. My work is not really focused on using any observations or conducting field campaign or anything. So we try not to focus too much on this aspect, and we used what was commonly used in the literature, which is the basic transfer function from the linear theory. It was pointed out at some point that maybe we should try to maybe verify with other methodology, for example, the ones that the higher order or just a different methodology to make sure that the linear reconstruction was satisfying enough, but we haven't tried that yet. And regarding the grid size, the thing is the domain is actually quite large. It goes from it extends 2.5 kilometers in the core direction and 3.5 kilometers in the longshore direction, and there are more than 700,000 grid cells. And we didn't try to go lower than that, because otherwise it would just become way too expensive in terms of computational time. And we conducted some experiments on the first experiment that I showed you. We conducted a study about the grid size, and we tried to define a parameter that would compare that would basically relate the swash extension to the grid size, and we tried to match our conclusions of the paper with the grid size that we used here on the site. And so we haven't tried lower grid size. Maybe lower grid size would compensate for the underestimation that we see in the swash, but at what computational cost? I don't know. I don't know if it's maybe I could try it just on one event or two just to verify, but I don't know. I don't think I will be able to run it on all the events that I made, because we had 3 days of data, and I've modeled one event every half an hour. So that's already a lot of events, and I don't think it would be way too long to have a let's say 1 meter grid size. It would be way too small.
Okay. Are there any more questions or remarks? I have maybe one. So can you go back to slide 19, where you mentioned yes, here. So here you mentioned this overestimation that you see here on the right part of the plot. So is it possible that this is due to the particular Pussinesque mode that you're using, or?
No, I don't think so, because we also saw it in so the what we use as input is the spectral outputs from SWAN, and the SWAN model was in fact much larger than the Bose numerical model and domain, sorry, and the civil location was included in the model. Well, obviously it went all the way to the coast, and we also observed the same overestimation at the civil location. So we observed it in the spectral model and also the observing depth average model that is both. So
so something different, yes, definitely.
Okay, can go back to this one slide. No, sorry, where was it? You showed spectra. So I mean, you have to understand the input for the Bose model, for the phase resolution model, is actually a SWAN spectrum.
Okay.
Time series, and you can see that at the offshore gauge here on the left side, there's quite a strong discrepancy. Overall, the shape of the spectrum significant wave height peak period is okay, and that's why probably also the transition of the energy and the runup comes out nice. But there's this double peak in the observation, which very likely corresponds to a standing wave in the bay, not captured by SWAN at all. So this goes back to what I said in the end. I mean, we get really, really good computations, even with a simple numerical model, and as long as all the boundary conditions are known. But this is something we start already with some kind of limitation, and that limitation propagates all the way through. And it's very difficult to get rid of that.
Okay.
Can I make a quick comment, Mario? This is Stefan.
Yes, go ahead.
Nice work. Just a couple of comments. So we used FunWave to do phase resolve simulations around the Narragansett Beach area for the Sandy hurricane, which had an 8-meter significant wave height offshore. And we observed significant differences going from 4 to 2 meters in resolution. But our experience was that we were actually underestimating the significant wave height with a coarser grid. And also what mattered was how far in the, offshore you could initialize the model, because it all depended on also, the dispersive properties of the model.
Yes.
Of course, FunWave was fully nonlinear. Bose is weakly nonlinear, but I don't think that makes a huge difference. But definitely there is an effect of grid, and and for us, most of the time we were losing too much energy. So it was not what you observe where you have too much energy. Also, bottom friction may be a factor. So I don't know what you used. If you have micro roughness in the beach, that would cause a larger bottom friction than anticipated. Perhaps that could be a factor. I don't know.
Yeah, the beach is a sandy beach, so it's rather uniform along the beach. We don't have these locations where I don't think the friction factor would be bigger. We used it was a Manning coefficient of 0.02. 0.02, and
it's called sand.
Yeah, I tried as well lower, and but it didn't have too much impact. No, the impact was actually smaller than I thought, especially on the swash. So we just kept the basic 0.02 for sandy beaches coefficient.
But thanks for raising the point, Stefan, with the diffusivity.
Yeah.
That's definitely an issue that we also found. We've updated the code to be very low diffusive. I'm actually using a couple of 2 different numerical schemes, something more like finite difference upwind on the outer part, and then in the SERP zone, a shock capturing Riemann solution, which helps to reduce the diffusion. But here, for example, we start in relatively shallow water, which reduces the problem of diffusivity during the propagation, but at the same time, we have to rely on SWAN spectrum at that depth, and 17-20 meters is certainly a depth where the waves have undergone refraction shoaling, and these effects are then not computed in the phase resolution model. So it's, as you mentioned, it's basically a trade-off of reducing errors, and it takes a lot of experience, practice. I think many models actually have similar issues.
Yeah. Yes. So to this, so something that related to the question of Kevin Martin. So you could at least try to change, I mean, refining the mesh for this one model, which was relatively coarse. It looked like anyways.
Which we did, what was it, 10 meters? For the input for that one? 20?
No, I think it was bigger.
Was bigger, okay. Yeah. We've seen that even with the spectral model, if you refine the mesh, and we've refined in some cases down to 10 meters, you can accentuate these refraction hotspots better and better. So the positive side of phase average model is that you can run it on relatively coarse grids, and you get reliable answers. But if you want the accuracy, you almost have to refine phase average model to the wave phase. That's quite interesting. Then you might as well just go with the phase result model. Huh? So,
okay, thank you.